Our universe might have been born from a violent crash with another reality. We will explore 20 provocative theories about colliding universes, a journey that will permanently change how you see the fabric of existence. You will discover how these cosmic clashes could be the hidden force behind the Big Bang, the strange nature of dark energy, and the very laws of physics we take for granted. What if the faint glow of the cosmic microwave background holds the scars of an ancient impact? Could the mysterious dark flow of galaxies be a gravitational pull from a cosmic neighbor? By the end, you will see the cosmos not as a lonely island, but as a dynamic arena of interacting realities. What does it mean for our place in the cosmos if we are not alone? Our cosmos might be a single bubble in a frothing sea of reality. This is the first theory, built on a concept called eternal inflation. Imagine a vast, primordial substance, a cosmic energy field that is forever expanding at an impossible speed. Within this churning expanse, pockets of this energy can suddenly decay, collapsing into a more stable state. Each of these collapses triggers a rapid, violent expansion, birthing a new universe in a process known as bubble nucleation. Our entire observable cosmos, with all its galaxies and stars, is just one of these bubbles. Now, in this infinite, bubbling foam, these newborn universes are not isolated. They drift and expand, and sometimes they bump into each other. A collision between two of these cosmic bubbles would be an event of unimaginable power. The energy released would be catastrophic, reshaping the very fabric of both realities. According to this idea, pioneered by physicists like Alan Guth, such collisions are not cosmic accidents. They are a fundamental part of how the multiverse evolves. The shockwave from an impact with a neighboring bubble universe could have even been the trigger for our own Big Bang, setting our entire cosmic history into motion. But how could we ever find evidence for such a spectacular event? The answer might be written in the oldest light we can see. The cosmic microwave background radiation, that faint afterglow from the universe's infancy, might hold the scars. Strange, unexplained patterns in this radiation, like cold spots or unusual ripples, could be the permanent bruises left by a long-ago collision with another reality. This theory transforms our universe from a solitary creation into a citizen of a bustling cosmic metropolis, forever marked by its neighbors. Our universe might not be a free-floating bubble, but a vast, three-dimensional sheet adrift in a higher dimensional reality. This is the second theory, rooted in the complex world of string theory, where our entire cosmos is a membrane, or a brane for short. Picture our reality as an immense, flat surface, like a single slice of an infinite cosmic loaf of bread. And just as other slices exist parallel to it in the loaf, other branes could be floating alongside ours in a hidden, higher dimensional space. The ekpyrotic model proposes a dramatic origin for everything we know. It suggests our Big Bang was not a spontaneous eruption from nothing, but the shattering aftermath of a collision between our brane and another one. This cosmic crash would have released an unfathomable amount of energy, instantly flooding our newborn universe with the searing heat and density we now call the beginning. Physicists like Paul Steinhardt and Neil Turok developed this idea into something even more profound, a cyclic model of the cosmos. In this view, the universe has no true start and no final end. Instead, it undergoes endless cycles. Over trillions of years, two branes slowly drift apart after a collision, the universe within them expanding and cooling. Then, drawn together by an unseen force across the higher dimensions, they eventually collide once more. Each impact is a new Big Bang, a grand reset of the cosmic clock that wipes the slate clean for a new cycle to begin. This offers a beautiful alternative to the mystery of a singular starting point, a cosmological singularity where the laws of physics break down. It suggests our entire history is just one chapter in an eternal story of collision and rebirth. So what traces would such a monumental, cyclical event leave imprinted on our reality today? A universe could die and be reborn from its own ashes. This is the third theory, known as Conformal Cyclic Cosmology, a vision crafted by the Nobel laureate Roger Penrose. It proposes a cosmos without true beginning or end, but with a series of distinct lifetimes called eons. Our universe, from the Big Bang to its ultimate fate, is just one eon in an infinite chain. In the far, far future, when all stars have burned out and even black holes have evaporated, the universe will be an empty, cold sea of massless particles like photons. According to Penrose's mathematics, this vast, sparse, and cold end state becomes mathematically identical to the hot, dense, and tiny beginning of a new Big Bang. The end of one eon seamlessly transitions into the start of the next. The collision here is not between two objects in space, but a meeting across time itself, where the final state of one universe becomes the initial condition for its successor. This elegant idea completely avoids the problem of a cosmological singularity, that point of infinite density where our current laws of physics simply break down. Instead, the universe resets through a process of transformation, preserving information from one eon to the next in a cosmic cycle of renewal. But how could we possibly find evidence for a universe that existed before our own? Penrose and his colleagues believe they have found it. They point to strange, concentric circular patterns etched into the cosmic microwave background, the oldest light in the sky. These features, which they call Hawking points, are hypothesized to be the imprints of unimaginably powerful bursts of energy, the source, the final evaporation of supermassive black holes from the previous eon. These ghostly rings are like echoes from a time before time, signatures of a reality that existed before our own Big Bang. Finding them is a monumental challenge, pushing our telescopes and data analysis to their absolute limits. It hints at a cosmos of breathtaking scale, where our entire history is merely one chapter in an eternal story written across countless eons. The orderly laws of physics we rely on might be nothing more than a temporary truce. Deep within the bizarre rules of the quantum world, reality is a blur of all possible outcomes happening at once. This is the foundation of our fourth theory, the quantum multiverse. The famous many worlds interpretation takes this idea to its ultimate conclusion. It proposes that every single quantum event, every random decay of a particle or the flip of a coin, does not just have one result. Instead, the universe splits, spawning a near-infinite number of parallel realities where every possible outcome actually occurs. In this breathtaking vision, there is a universe where you took a different job, a universe where the dinosaurs never went extinct, and a universe where the laws of physics are entirely different. In this sea of possibilities, a collision is not a physical crash of two giant objects. It is a quantum decoherence event, a violent and sudden disentangling of two branches of the multiverse that were once linked. Think of it like two radio stations broadcasting on the same frequency, creating static as their signals overlap. Now, imagine that interference happening to reality itself. When two of these parallel worlds decouple, the delicate quantum connection that once bound them snaps. The result could be a fundamental and jarring shift, localizing their realities into separate, distinct streams. What would such a quantum divorce look like from our perspective? It might not leave a scar in space, but it could fundamentally alter the rules of the game in a specific region. Physicist David Deutsch argues that these parallel worlds are ontologically real, meaning they truly exist and are not just mathematical tools. He suggests that information could, in principle, leak from one branch to another. A collision or a moment of intense quantum interference could allow such a crossover. The consequence: we might discover a pocket of space where the strength of gravity is slightly weaker, or where a new type of exotic matter spontaneously appears, defying everything we know. This quantum perspective forces a profound question. What is a universe, really? If every possibility blooms into a full-fledged reality, then a collision is not a meeting of strangers, but a sudden, jarring separation of two versions of what was once a single, coherent whole. The very constants that govern our existence could be the fragile result of one such ancient quantum split. Galaxies are drifting on a mysterious current. Across the cosmos, vast clusters of galaxies are all moving together in a coherent stream, pulled toward a single point on the sky. Astronomers call this the dark flow, and it is a profound enigma. The gravitational pull from all the visible matter in our known universe cannot account for it. Something immense is tugging on these galaxies from beyond the edge of our cosmic map. The most startling explanation is that the source of this pull does not even exist within our universe. It could be the gravitational influence of a colossal structure in a neighboring reality, a parallel universe so massive that its gravity leaks through the higher dimensional space or the bulk that separates us. This is not a collision of matter, but a gentle, persistent drag, a sign that our universe is not an island. We are being jostled by external cosmic forces, like a boat on a pond feeling the wake from another vessel just out of sight. Data from observatories like the Planck satellite have meticulously analyzed this peculiar motion, searching for its pattern and origin. If this interpretation is correct, then the dark flow is the most direct evidence we have ever glimpsed of another cosmos. It is a pointer to a cosmic neighbor, a universe so close we can feel its gravitational breath. This single idea shatters a foundational pillar of modern cosmology, the cosmological principle, which states that the universe should look roughly the same in every direction on a large scale. A coherent flow toward one specific region defies that expectation. It opens the door to even stranger gravitational phenomena, suggesting that the forces we consider fundamental might be local laws, unique to our own cosmic bubble, and easily influenced by the activity next door. Our reality might be a cosmic illusion, a three-dimensional projection from a two-dimensional surface at the very edge of space. This is the sixth theory, the holographic principle, and it completely redefines what a universe even is. Think of it like a movie. The rich, three-dimensional world you see on the screen does not actually exist inside the projector. It is all encoded on a flat, two-dimensional film. In the same way, our universe, with its galaxies, stars, and our own bodies, might be a magnificent projection. All the information needed to create everything we experience could be stored on a distant, spherical surface that surrounds us. This idea, championed by physicists like Leonard Susskind, emerged from a deep puzzle about black holes and how they preserve information. It suggests that the fundamental building blocks of reality are not particles or forces, but bits of information. Now imagine what happens in this strange framework when two universes collide. It would not be a cataclysmic smash of planets and stars. Instead, it would be an interaction between their two-dimensional boundaries, a merger or an exchange of cosmic data. The projection we call reality would experience a glitch in its source code. The laws of physics within the affected volume could be rewritten. Suddenly, a region of space might operate with different rules, where entropy, the measure of disorder, behaves in reverse, or where particles become instantly and mysteriously linked across vast distances. Finding such an anomaly would be like discovering a patch of the sky where the programming has been altered, a permanent error in the matrix of our universe. This transforms a cosmic collision from a physical event into an informational one, where the very source code of reality receives an update from an external system. What would it mean to live inside a reality whose fundamental rules are not fixed, but were merely set by the last day to exchange with another cosmic server? Dark energy, the mysterious force accelerating the expansion of our universe, might be a cosmic ghost. The seventh theory suggests this enigmatic push is not a fundamental property of empty space, but the fading echo of a long-ago collision. Picture the aftermath of that monumental impact, a shockwave of pure repulsive force rippling through the very fabric of space-time. This wave would have given our universe an immense outward shove, a push that never truly stopped. Instead of a constant, unchanging force, dark energy could be a transient phenomenon, slowly dissipating over billions of years like the dying reverberations of a colossal bell. In this model, the specific properties of dark energy, its density and its peculiar repulsive strength, are not arbitrary numbers. They are direct calculations, the unique signature of that initial impact, determined by the mass and speed of the universe that struck our own. This completely reframes one of cosmology's greatest puzzles. Dark energy is no longer a mysterious fixture of the cosmos, but a historical artifact, a cosmic memory of a violent encounter that sealed our ultimate fate. If this is true, then by meticulously studying the rate of expansion today, we are not just measuring a force, we are forensically reconstructing the moment of contact itself, peering back into the very instant our reality was forever changed by a neighbor we can no longer see. Our universe seems suspiciously perfect for our existence. Its fundamental forces are balanced on a razor's edge, a cosmic coincidence known as the anthropic principle. If gravity were slightly stronger, the universe would have collapsed back on itself long ago. If the nuclear forces were weaker, stars could never have forged the elements of life. This fine-tuning is one of the deepest mysteries in all of science. The eighth provocative theory offers a startling explanation, rooted in the violence of colliding universes. Perhaps our cosmos is not a one-off miracle, but a survivor of a brutal process of cosmic natural selection. In this speculative vision, universes are born, they collide, and they reproduce. When two cosmic realities slam together, the resulting shockwave does not just create a new Big Bang. It can also reset the fundamental parameters of physics for the newborn universe. The constants of nature, the strength of gravity, the mass of an electron, all are shuffled like a deck of cards at the moment of impact. Most of these newly created universes are stillborn. Their laws are chaotic, their forces unbalanced. They collapse instantly or expand into cold, empty voids where no atom can ever form. But by pure chance, a tiny fraction of these cosmic offspring emerge with just the right conditions for stability. They can form galaxies, stars, planets, and eventually, conscious life that can look back and wonder at its own existence. This idea, echoing the work of physicist Lee Smolin, transforms our perspective entirely. We do not live in a random universe. We inhabit a cosmic winner, a universe that was shaped by a long lineage of violent collisions, each one selecting for the stability and complexity necessary for life to arise. It provides a powerful, non-theistic answer to the question of why the world is so hospitable. Our existence is not a lucky accident, but the probable outcome of a vast, multiversal evolutionary process where only the fittest realities endure. This suggests that the very laws we take for granted are not fundamental truths, but merely the local bylaws of a universe that successfully passed the ultimate test. The very ground of being upon which our universe is built could be a temporary illusion. We exist in a state of deceptive stability, a condition physicists call a false vacuum. Imagine a valley nestled high in a mountain range. It feels stable and secure, but there is a much deeper valley far below. Our universe is simply resting in that high valley. It is a local energy minimum, stable for now, but not in the absolute lowest energy state possible. All it would take is a sufficiently powerful nudge to push a small region over the mountain pass and into the true vacuum below. A collision with another universe could be that cataclysmic nudge. The immense energy released at the point of impact could provide the necessary shock, creating a single, microscopic bubble of this true vacuum state. This bubble would then begin to expand in all directions, moving at the speed of light. This is the terrifying process of vacuum decay. The boundary of this expanding bubble would not be a physical wall, but a wave of total transformation. As it passes, it would rewrite the very laws of physics in its wake. The fundamental constants that govern reality, the strength of gravity, the nature of matter, everything would be permanently and irrevocably altered. The new laws established within this true vacuum state would almost certainly be incompatible with the existence of atoms, stars, planets, or life as we understand it. This would not be an explosion that destroys things, but a silent, swift change that redefines the meaning of destruction itself. The silent, empty voids between galaxies, which we see as pockets of nothingness, might not be empty at all. They could be the calm before a storm, the quiet regions waiting for a trigger from an unseen cosmic neighbor to initiate the final, unstoppable rewrite of our reality. A collision between universes would forge relics of impossible physics. The 10th theory proposes that such an impact could have generated stable forms of exotic matter, creating permanent scars in the fabric of our reality. These are not ordinary particles, but bizarre objects known as topological defects, fossilized remnants of a more chaotic, violent era. The concept is like cooling water. When water freezes, its molecular structure shifts from a fluid state to a rigid crystal. But sometimes the transition is imperfect. Bubbles of air get trapped, or the ice forms with tiny cracks and fissures. These imperfections are the topological defects of the ice. Now, imagine the entire universe undergoing a similar phase transition in the searing aftermath of a cosmic collision. As the fiery chaos of the impact cooled and settled into the orderly cosmos we know today, the process might not have been perfectly smooth. Certain structures, defects in spacetime itself, could have been frozen into existence. Among the most intriguing of these relics is the magnetic monopole. In our everyday world, every magnet has both a north and a south pole. Cut a magnet in half, and you get two smaller magnets, each with its own pair of poles. A magnetic monopole, however, would be a fundamental particle that is just a north pole, or just a south pole, a solitary, isolated magnetic charge. Its existence is predicted by many grand unified theories, but we have never found one. If discovered, it would be a monumental breakthrough, and its origin could very well be a collision that twisted the electromagnetic field of our infant universe into a stable knot. Even more immense are cosmic strings. These are not strings in the everyday sense, but unimaginably dense, one-dimensional floors in spacetime, thinner than a proton but with the mass of an entire galaxy. A single cosmic string stretched across the cosmos would have a gravitational field so powerful that it could act as a lens, warping the light from distant galaxies behind it. It might even have left a distinctive signature in the cosmic microwave background, a sharp, linear tear in the ancient light. These defects are more than just cosmic curiosities. They could have been the very scaffolding upon which the universe was built. their immense gravitational pull would have acted as seeds, attracting the primordial hydrogen and helium, funneling matter into the vast filaments and clusters of galaxies we observe today. The search for these objects is a direct hunt for evidence of a collision. Finding a magnetic monopole in a particle detector or spotting the unique gravitational lensing of a cosmic string would be like finding a piece of shrapnel from the moment of impact. It would tell us that the fundamental architecture of our cosmos, its grandest structures, were carved by a violent meeting with another reality. The silent hum of the cosmos might hold the loudest evidence of all. Our 11th theory proposes that the earliest instance of our universe, the searing chaos of the Big Bang, should have generated a faint background of primordial gravitational waves. These are not waves of light or sound, but ripples in the very fabric of spacetime itself, a relic echo from the beginning of everything. A collision with another universe would have been an event of such staggering energy that it would have shaken the foundations of reality, sending a powerful, unique surge through this cosmic background. Think of it like listening to the quiet static of a detuned radio. Most of the noise is random, but then you hear a distinct, sharp crackle that stands out from the rest. A universe-scale collision would produce a similar spike, a characteristic bang hidden within the gentle hum of the universe's oldest vibrations. Future observatories like the Laser Interferometer Space Antenna, or LISA, are being designed to listen for these whispers. This ambitious project would consist of 3 spacecraft flying in a perfect triangle millions of kilometers apart, using lasers to detect the infinitesimal stretching and squeezing of space as a gravitational wave passes by. While current detectors like LIGO are tuned for the violent chirps of merging black holes, LISA would be sensitive to the lower frequency waves from the universe's infancy. The signature of a cosmic collision would be unmistakably different. It would not be the quick, rising tone of 2 stars spiraling together. Instead, it would be a model-dependent fingerprint, a specific pattern of waves dictated by the energy, angle, and nature of the impact itself. Finding this signal would be like discovering a fossilized recording of our own birth. It would transform the search for gravitational waves from an exploration of stellar cataclysms into a direct hunt for our cosmic origins, providing a soundtrack to the very moment our reality was forged in a violent meeting with another. The sudden arrival of another reality could have been the master sculptor of our universe's infancy. Cosmic inflation, that brief moment of unimaginable expansion just after the Big Bang, might not have been a solitary event. It could have been dramatically reshaped by a collision. Imagine our newborn universe as a balloon being inflated at a frantic, exponential rate. A collision with a neighboring cosmic bubble would be like a giant hand suddenly squeezing that balloon. The result would be a profound and immediate modification of the entire inflationary process. The impact could have injected a massive surge of energy, like a turbocharger kicking in, forcing the inflation to continue for far longer than it otherwise would have. This would have stretched the fabric of our reality even smoother, directly creating the remarkably flat and uniform cosmos we observe on the largest scales. Alternatively, the collision might have been the very event that brought inflation to an abrupt and definitive end. The shockwave from the impact could have violently transferred its energy into the universe, a process known as reheating. This sudden injection of heat would have flooded the cosmos with the hot, dense soup of particles that eventually coalesced into every galaxy, star, and planet. Our entire material world might owe its existence to the cataclysm that stopped the universe from inflating itself into a cold, empty void. The evidence for this dramatic interaction could be written into the oldest map we have. The subtle variations in the cosmic microwave background, the tiny temperature differences that seeded all future structure, might not be purely random quantum fluctuations. They could be the permanent imprints of that long-ago impact, the cosmic bruises and wrinkles left by the touch of another universe. This idea forever links the grandest scales of our cosmos to a singular, violent encounter, suggesting that the very geometry of our reality was forged in a meeting of two worlds. The barrier between worlds might be far less solid than we ever believed. Our 13th theory pushes the quantum multiverse into a startling new light, proposing that cosmic collisions are not singular, explosive events. Instead, they are a constant, gentle hum, a perpetual resonance between parallel realities. This is the idea of many worlds quantum resonance. In this view, the infinite branches of the multiverse do not simply drift apart in silence. They vibrate against one another, their quantum wave functions subtly interacting like overlapping sound waves. This low-level resonance creates a continuous, almost imperceptible exchange of information and energy. It is a soft collision happening everywhere, all the time, woven into the very fabric of quantum reality. We might already be seeing its fingerprints in some of the strangest behaviors of the subatomic world. Take quantum tunneling, for instance, where a particle seemingly teleports through an energy barrier it should not be able to cross. Could its success sometimes be boosted by a faint nudge from a parallel universe where the barrier was just a little weaker? Or consider the statistical anomalies in particle physics, where the outcomes of experiments show tiny, unexplained deviations from what probability dictates. These could be the subtle echoes of countless other versions of the experiment being conducted in adjacent realities, their results subtly bleeding into our own. Detecting this multiversal crosstalk directly would be a monumental challenge. It would require exquisitely precise quantum experiments, perhaps using ultra-cold, isolated systems designed to shield them from all known local influences. The goal would be to observe an effect that has no cause within our conventional understanding of space and time, an influence that comes from outside our causal cone. This theory suggests that we are not isolated citizens of a single universe, but perpetual participants in a vast, whispering network of realities. The walls between the worlds are porous, and we exist in a state of continuous, gentle contact with an infinity of other versions of ourselves. Our universe might be spinning. The 14th provocative theory suggests a glancing blow from another reality could have set the entire cosmos into a slow, majestic rotation. Most foundational models assume our universe is the same in every direction, a principle of perfect isotropy. But what if that is not entirely true? A collision would not have to be a direct head-on impact. A sideswipe from a passing cosmic brain could have transferred a tremendous amount of angular momentum, imparting a net spin to the very fabric of space-time on the largest imaginable scale. This universal rotation would create a subtle but definitive preferred direction in space, a cosmic north that everything from galaxy clusters to the background radiation itself would subtly reference. The hunt for this spin is already underway, a meticulous search for the faintest of fingerprints. Astronomers scrutinize the polarization, or the specific orientation, of the light from the cosmic microwave background, looking for swirling patterns that could only be explained by a rotating universe. They also study the alignment of billions of distant galaxies, searching for a coherent twist in their distribution that defies random chance. Finding such an anisotropy would be one of the most profound discoveries in the history of science. It would not merely add a new fact to our books, it would shatter a core pillar of modern cosmology, forcing us to rewrite our most basic assumptions about the cosmos. A detected rotation would be a direct pointer to an external cause, a cosmic push from a neighbor that set our entire reality spinning like a top. It would mean our universe has a specific orientation within a grander metacosmos, a permanent relic of a dynamic interaction that occurred before time as we know it even began. Two universes could be bound together in a ghostly embrace, linked from the moment of their birth. This 15th theory proposes an entangled universe genesis, where our cosmos and a twin reality were born from a single, spontaneous quantum fluctuation. In the same way that two particles can be created as a linked pair, sharing a single quantum state no matter how far apart they drift, our entire universe might have a perfect mirror, a cosmic sibling born from the same primordial spark. The collision here is not a violent impact but an unbreakable, non-local connection. It is spooky action at a distance but on the grandest possible scale. Changes in the fundamental quantum fields of one universe could resonate instantaneously in the other, a synchronization that defies our understanding of space and time. Imagine if the formation of a massive galaxy cluster in our reality was mirrored by the simultaneous appearance of a similar structure in the twin universe, a correlation with no possible causal link within the confines of spacetime. The vacuum of space itself, with its faint, seething energy, might pulse in perfect, inexplicable harmony with its invisible counterpart. The profound challenge, of course, is that we are trapped inside one half of this cosmic pair. We can only observe our own universe, forever wondering if the patterns we see are truly our own, or if they are the faint echoes of decisions made in a reality we can never directly visit. How could we ever detect such a connection? The key might lie in searching for statistically impossible correlations, patterns in the large-scale structure of the cosmos or in the cosmic microwave background that are so coherent, so perfectly arranged that they cannot be explained by any local physical process. This idea takes the profound weirdness of quantum mechanics and projects it onto the canvas of the entire cosmos, suggesting that the entanglement we see in the lab is not a small-scale curiosity. It is the fundamental principle that governed the very first instant of creation, forever binding our fate to that of a stranger we can never meet. The very rules of reality might be a local ordinance. Our 16th theory confronts a cornerstone of modern physics, the assumption that numbers like the fine structure constant are truly constant. This number dictates the strength of the electromagnetic force, governing how atoms bind and light interacts with matter. It is a silent, unchanging pillar holding up our entire physical world. But what if that pillar is not as steady as we believe? A collision with another universe could have sent a shockwave through the fundamental fields of our cosmos, a wave of such profound energy that it temporarily warped the very parameters of physics in its wake. As this wave expanded, it would have created vast, bubble-like domains where the laws of nature were subtly, or perhaps drastically, different. In one region, the fine structure constant might have been a fraction of a percent stronger, making chemical bonds more rigid. In another, it might have been weaker, leading to atoms that are more easily torn apart. These domains would have borders not in space but in the laws themselves, frozen into the fabric of the universe as the shockwave passed and the cosmos cooled. We are hunting for the ghosts of these borders today. Astronomers point their most powerful telescopes at the most distant quasars, the brilliant cores of ancient galaxies whose light has traveled for billions of years to reach us. By analyzing the specific absorption lines in this fossil light, they can measure the value of the fine structure constant at the time and place the light passed through interstellar gas. A single, definitive measurement showing a different value would be the scientific equivalent of an earthquake. It would mean that the laws of physics are not universal truths, but more like regional dialects set by the chaotic aftermath of a long-ago impact. Finding such a variation would be like discovering a chapter in our cosmic history written in a different language, a permanent testament to the moment an outside force reached in and changed the rules of our game. A gateway to another reality could have just opened in the depths of space. The 17th theory envisions our cosmos connected to others through cosmic plumbing, where a black hole in one universe is linked to a white hole in another. According to some elegant solutions to Einstein's equations of gravity, a black hole's relentless pull might not end in a singularity of infinite density. Instead, it could form a tunnel, a wormhole, that exits somewhere else as its perfect opposite. A white hole is a region of spacetime that can only eject matter and energy, a cosmic fountain that nothing can ever enter. A collision between universes in this model would not be a broadside smash of two branes. It would be a precise, channeled event where a catastrophe in a neighboring reality triggers a sudden appearance in our own. Imagine a supermassive black hole in that other universe undergoing a violent collapse or merging with another. The immense energy and matter consumed by that event would have to go somewhere. The wormhole connection would act as a relief valve, funneling that cataclysmic output through the white hole exit and into our cosmos. From our perspective, it would look like a sudden, point-like eruption of energy with no apparent cause, a miniature Big Bang blossoming from the void. This theory provides a stunningly elegant mechanism for how universes can exchange material and information without ever physically overlapping in a higher dimensional space. We would not see the collision itself, only the delivery of its aftermath. Astronomers scanning the skies for such an event would be looking for the ultimate anomaly, a new, brilliant source of energy that simply appears without a progenitor star or galaxy. It would be a cosmic message in a bottle, a shard of a distant reality's death throes delivered directly to our doorstep. Finding such an object would confirm that the universe is not just interactive, but intricately plumbed with hidden connections threading through the multiverse. Our reality might be running on borrowed processing power. This 18th theory takes the collision of universes out of the cosmos and into the computer, framing our existence through the lens of the simulation hypothesis. Philosopher Nick Bostrom proposed we might be living in an advanced civilization's digital creation, a universe meticulously coded to emulate every law of physics. In this view, a collision is not a gravitational smash or a quantum split. It is a software conflict, a glitch caused by two complex simulations running on the same cosmic scale hardware. When these two virtual realities interact, their data streams could bleed into one another, creating observable errors in the fabric of our world. We might detect these as profound statistical anomalies in particle accelerator data, where the outcomes of millions of collisions defy probability in a way that points to an external source of randomness. Or we might find impossible geometric structures, crystals that violate the known symmetries of nature, or fleeting moments where energy or momentum is not conserved, as if the simulation briefly lost track of its own accounting. These events would be the equivalent of a buffer overflow or a memory leak between two running programs, where the data from one universe spills over and corrupts a small section of the other. While this idea is one of the most speculative we have encountered, it fundamentally recasts the nature of a cosmic collision. It transforms it from a physical event into a computational artifact, a bug in the matrix. The search for such glitches then becomes something far more profound than astrophysics. It becomes a direct test of the simulation hypothesis itself. Every strange, unexplained event in our cosmos becomes a candidate, a potential clue that we are not just looking at the laws of nature, but at the source code of a reality someone or something built. Finding a verifiable glitch would be like discovering a comment left in the programming, a signature from the architect of our existence. It suggests that the collisions shaping our world are not random acts of cosmic violence, but the inevitable side effects of a system running multiple instances of reality on a single, unimaginable server. Dark matter could be the cosmic inheritance from a universe that died long ago. This 19th theory reimagines the mysterious substance that binds galaxies together not as a leftover from our own Big Bang, but as a direct product of a previous cosmic cycle. In the grand vision of a cyclic universe, our eon did not begin from nothing. It was born from the collapse of a prior reality, a cataclysmic event often called the Big Crunch. The unimaginable pressures and temperatures of that final collapse, followed by the shattering violence of the collision that sparked our own Big Bang, would have been a forge of incredible power. Within that crucible, stable, massive particles could have been created, particles that interact so weakly with ordinary light and matter that they have remained almost entirely invisible to us. These relics from the end of time in a previous universe became the dark matter that dominates our own. This idea forges a profound link between the two greatest puzzles in all of cosmology. The origin of our universe and the nature of dark matter are not separate mysteries. They are different chapters of the same eternal story. One explains the other. The gravitational scaffolding upon which every galaxy formed, the invisible halo that keeps stars from flying apart, is not a feature unique to our reality. It is a ghostly structure built from the ashes of a cosmos that came before. This leads to a stunning prediction. If this theory is correct, then the specific properties of dark matter particles, their mass and the way they interact, are not random. They are a direct signature, a frozen record of the specific conditions present during the Big Crunch and the subsequent collision. They hold the precise physics of that terminal moment. This means that our ongoing, painstaking hunt to detect dark matter in deep, underground laboratories is about more than just identifying a new particle. It is an archaeological dig into the history of existence itself. Successfully capturing a dark matter particle and measuring its characteristics would be like recovering a fossil from a previous incarnation of reality. It would give us our first tangible piece of evidence about the universe that gave birth to our own, revealing the physical laws that governed a cosmos lost to time. Our own inner awareness could be the final echo of a cosmic collision. This 20th and final theory is the most speculative of all, proposing that consciousness is not a latecomer to the universe, a mere accident of biology. Instead, it is a fundamental feature of reality, as intrinsic to the cosmos as space and time. In this view, a collision between universes would be more than a physical or informational event. It would be a meeting of different realms of mind, a clash of conscious spheres or new spheres. The profound mystery of why our universe seems so perfectly fine-tuned for life finds a radical answer here. Perhaps conscious observers are not just passive beneficiaries of this cosmic luck. We are active participants necessary to stabilize a wobbly, newborn reality in the chaotic aftermath of an impact. This is the essence of the participatory anthropic principle. The universe requires an audience to bring it into full being, to pin down its fuzzy quantum possibilities into the concrete world we all share. The violent shock of a cosmic collision could have imbued the very fabric of our reality with the potential for self-awareness, seeding the cosmos with the raw materials of mind. From this perspective, the long, slow evolution of life, leading to brains complex enough to look back at the stars and wonder, was not a random fluke. It was an inevitable outcome, a destiny written into the universe's birth certificate at the moment of its traumatic creation. This idea builds a breathtaking bridge between the cold, hard mathematics of cosmology and the intimate, warm mystery of our own thoughts. It suggests that your ability to feel, to wonder, and to ask these very questions is deeply connected to that primordial drama of colliding worlds. The outer cosmos and our inner experience are not separate. They are two sides of the same reality, forever linked by an event that set the stars in motion and awakened the universe to itself. The notion that our universe is not alone feels like a modern revelation, yet it echoes through thousands of years of human thought. Ancient Greek philosophers like Epicurus argued for the existence of innumerable worlds, asserting that in the infinite void, countless cosmic arrangements must naturally form. Meanwhile, ancient Hindu scriptures described a cosmos in perpetual, rhythmic cycles of creation, preservation, and destruction, a concept strikingly similar to modern cyclic universe models. These were not scientific theories in our sense, but profound philosophical and spiritual intuitions about the nature of reality. They show a deep, persistent human urge to look beyond the horizon of our own world and consider a grander stage. The journey from that ancient speculation to our current scientific pursuit is a monumental leap. For centuries, these ideas remained in the realm of metaphysics, beautiful but untestable thought experiments. The transformation began when mathematics and observation provided the tools to frame these age-old questions in a new language. The inflationary multiverse, the ekpyrotic scenario, and quantum many worlds are not just whimsical stories. They are rigorous mathematical structures that make specific, falsifiable predictions about what we should see in the cosmic microwave background or the distribution of galaxies. This shift marks a pivotal moment in our intellectual history. We are no longer merely wondering about other worlds. We are actively hunting for their fingerprints, using telescopes and particle detectors as our guides. This rich historical context adds a profound depth to our exploration. It reminds us that the drive to understand our cosmic context, to ask if we are part of something vastly larger, is a fundamental part of the human spirit. We are continuing a conversation that began with philosophers gazing at the stars, now armed with the power of modern science to find the answers. Our journey through these 20 theories leaves us with a cosmos that is profoundly interconnected and alive with possibility. The grand takeaway is that our universe is likely not a solitary, silent entity, but a participant in a far richer, more dynamic existence. From the gentle quantum resonance between parallel worlds to the shattering violence of colliding brains, these ideas collectively shatter the illusion of cosmic isolation. They force us to reconsider everything we hold as fundamental, suggesting that the very laws of physics might be temporary, local rules, specific to our own cosmic neighborhood rather than universal truths. This pursuit, while still in its infancy, pushes the boundaries of both science and philosophy. It asks us to blend the cold, hard data from our telescopes with the deepest questions about our own place in the grand scheme of things. While definitive proof for most of these theories remains just beyond our current grasp, the search itself is transformative. Each experiment, each new map of the cosmic microwave background, and each observation of distant galaxies is not just data collection. It is a deliberate probe into the nature of reality itself, a test to see if our universe bears the marks of its neighbors. These are not mere flights of fancy, but structured hypotheses grounded in the rigorous language of mathematics and a fearless spirit of inquiry. They represent humanity's enduring desire to look beyond the horizon and understand our true context. Let this exploration be a starting point for your own wonder. The next great cosmological revelation, the one that finally confirms we are not alone in the metacosmos, could be just one observation away. We would love to hear which of these 20 theories captured your imagination the most. Share your thoughts in the comments and subscribe to continue unraveling the deepest mysteries of the universe with us.